All right, this is a quick solution video for FRQ number 1 on assignment 10.2. Two ladybugs are standing on a rotating disc that's spinning counterclockwise. Assumes no friction on the outside, so there's no outside forces. Is the angular speed of ladybug A greater, less than, or the same? Angular speed, they are the same. Angular speed is the change in angular displacement with respect to time. Both A and B have same change in angular displacement with respect to time. Radius doesn't matter. +1, you have to be correct answer with correct explanation. Is the linear speed of A greater than, less than, or the same? A is greater. Briefly justify your answer. The linear speed is equal to its angular speed times r. So A's radius is greater. Its angular speed the same. Therefore, A's linear speed greater. +1. Got to be correct with correct explanation. The ladybug begins to walk in a circular path in the direction of the disc rotation. So the disc is rotating, I guess, that way. A starts to walk in that direction, right? Does the magnitude of the angular momentum of the disc alone, not the ladybug disc system, but the disc? Well, we know the momentum of the system has to stay the same. But what happened to the momentum of the bug? It went up because its velocity, its angular velocity went up. So the disc had to decrease. Why? You had to state the angular momentum of the system is constant, no outside forces, right? Because conserved, or because there's no outside surface. The angular momentum of the bug increased because its velocity increased, right? Therefore, the angular momentum of the disc had to decrease in order for it to stay the same. This is worth +2. Correct answer, correct explanation, so forth and so forth. All right, this situation, I have a whole bunch of data. We didn't even need this information they gave us, but they gave us this R value. What they give us? 0.9, and then it became 0.1, I believe. Yep, this is 0.1. Okay, R. The original momentum of moment of inertia was I initial, and the final moment of inertia was I2, so I1, I2. And they did tell us over here that this took 2.5 seconds per rev. If you look on your sheet, its angular velocity is 2 pi over t. And over here, they told us that its period was 2 seconds, 2 pi over t. Okay. Now, derive an equation for I2 in terms of I1. We know that the momentum initial has to equal momentum final. That equals the initial moment of inertia times its initial speed. And that must equal its final, which they called F2, times its final angular velocity, which they called, we'll call omega 2. So then we'll plug in some things that we know. Okay. I1, because we're trying to find an equation for I2 with respect to I1, so we can leave I2 and I1. we can rearrange this information about period, and we know that omega over here is equal to 2 pi over 2.5, and that equals moment of inertia 2, and that'll equal 2 pi over 2. 2 pi's cancel, divide those out, and I can rearrange for, what do we want to find? I can't remember. Derive an equation for I2. Okay, I2, I multiply 2 by both sides, and I get 2 over 2.5 equals I1, and that is the correct answer. And that was worth, I think, 2 points. 1 point for this, plus 1, and then 1 point for getting the correct answer. This next one, to be honest, I have a difficult time explaining. I don't know every single thing. But anyway, while the ladybug is walking towards the center of a disc, does it exert a torque on the disc? Well, what's happening to the disc's angular speed as the ladybug goes inward? Its angular speed is increasing. So it has to be. Now, I have a hard time explaining how that is, but it is. Just think of the disc. Is the disc increasing? Yes. And the answer is because the angular speed of disc is increasing. So it's got to be exerting a torque on the disc. All right, and that was just 1 point. And that's what I got.